Okay, so now we're on the 10th identity here. So we want to prove that the trace of gamma 5 times p1 slash p2 slash is 0. So again, we can pull out the momentum terms. We just have this trace here, gamma 5 times gamma nu, and of course that's all we have to look at. If it's going to be 0, it's going to be because the trace of this thing is 0. So all we have to do is, so we can't introduce a gamma 5 or a gamma 0, that doesn't work, because we wouldn't know whether, well, because we have this gamma 5, if we introduced gamma 5s, we'd anti-commute twice, and that wouldn't give us a minus sign, so we couldn't go anywhere from there. And then we can't do like a gamma 0 because it depends whether gamma mu or gamma nu is 0. But what we can say is that gamma mu and gamma nu could only ever take on, we could only have at most 2 different gamma matrices in this thing. So either, we could have gamma 0 and gamma 1, or gamma 1 and gamma 3, but we'll never have all 4. So what we're going to do is introduce a minus gamma alpha alpha, where gamma alpha is just whatever gamma matrix is not being used in this trace. So, for example, if it was gamma 1, gamma 2, we pick gamma alpha to be gamma 3. And so on. And I guess I'm assuming that it's one of the spatial ones, technically, because I'm introducing, so the spatial ones are, the square is -1, so I'm doing minus gamma alpha alpha, gamma alpha. So that's the identity. And then I just proceed in the same way I've done the last a few others. I just anti-commute, because gamma alpha anti-commutes with these, because it's different. And we'll anti-commute with gamma 5, so I can bring it all the way over. That anti-commutes 3 times, so I get a minus sign. Then I can permute it back over, and then this is -1, so I end up proving that this is minus itself. The next one is proving this thing. So this confused me at first because it involves this gamma mu with a lower index, and so it's not that there's another matrix gamma mu that has a lower index. It's that in this notation, what he really means, rather than saying, this thing, which would be, it would be like gamma 0 times p cross times gamma 0, or gamma 1, this, whatever. But instead what he means is that you should be summing over this index. So this should be, you do like a, 4-vector contraction kind of thing. So it involves all these 4 terms with the usual, time part as a plus sign, and the spatial parts have a minus sign. And but always involving, the gamma matrices with an upper index. So that's all that means. So knowing that, we can write out, so I just expand my my p cross, that's p nu, gamma nu, and then I can bring the p nu over. So I have this thing, and then I just want to anti-commute gamma nu and gamma mu, and that'll give me this, and so I'll end up with these 2 terms. And so gamma mu, that will just be gamma 0, or gamma 0 squared minus gamma 1 squared minus gamma 2 squared minus gamma 3 squared. And that will be 1 minus -1 minus -1 minus -1. So I get a 4. So that gives me 4 p mu gamma mu, or -4 p mu gamma mu. And then once I've, raised this thing here, that's 2 p nu gamma mu. And so I end up with a net -2 p cross. The next one, okay, so the next one we do the same thing, only this time we have two p crosses sandwiched in between. So we do the exact same thing. We just commute or anti-commute gamma mu over, and we get this, and then we have to do it another time to get it so it's next to the other gamma mu. And so I just end up with two terms. And again, I get a 4 and these things. And so this term is, oh, actually, okay. So this term and this term are the same. So these cancel. So I end up with the 2 there. But then these terms involve gamma nu, gamma sigma. But this term involves gamma sigma, then gamma nu. So I have to use the anti-commutation relation here to get, to flip these around. So the first term just comes from combining these two, and then the other two terms come from using the anti-commutation relation. And and from there we see that these cancel, and I'm just left with this, which is 4. After I contract these indices, it's 4p1.p2. And then I guess because Tong hates us, he wants us to do the same thing with 3 p crosses and show that this is minus 2 p3 cross, p2 cross, p1 cross. So this one's not very fun, honestly. You do the same thing that you just did with the other two problems. You just start anti-commuting this gamma mu across. You have to do it 3 times. And, you end up, after you've done all that, you end up with these 3 terms. And then you have to take kind of a look at the answer. So we see it's p3 cross, then p2 cross, then p1 cross. So the order of the operators is kind of flipped. So if I have, in this expression, it's gamma mu, or gamma nu, gamma sigma, gamma tau. In my final expression, I'll want a gamma tau, gamma sigma, gamma nu. And as you'll notice, none of these 3 terms that I've gotten here are the gamma matrices in the right order. So I have to anti-commute things to get it until they have, the right order of terms. So, you basically have to do a whole bunch of that. Once in this term, twice in this term, 3 fucking times in this term. But you can do it. You can do it. And you do find in the end that you're left with just this. So things, you get a bunch of terms, but they end up canceling out. So I'm just left with this, and of course I have my gamma tau in the front and gamma sigma in the middle, gamma nu at the end, so that's p3 cross p2 cross p1 cross times minus 2. So enjoy doing that if you have to do that. Then the last one is not as bad. I have to prove this. So we do the same thing, bring out my p's. I have the trace of gamma 5 times 4 gamma matrices. And one thing we can notice here is that if any of these are the same, if mu or if we had any repeated gamma matrices so that there was one unused gamma matrix, then we could use that unused gamma matrix to, insert an identity and then anti-commute. Because we have 5, an odd number of matrices here, and prove that it's 0 in the usual way. So that's that case. But then in the case where these are all different, so for example, 0, 1, 2, and 3, then we couldn't do that. But in that case, we would know that since they're all different, they all anti-commute. So if we permute, like cyclically permute these things, or anti-commute them, we get a minus sign. And based on those properties, we say that this trace has the same properties as this totally anti-symmetric, tensor epsilon mu nu rho sigma. Again, because if they're repeated, if we have repeated indices here, this is 0. And if we exchange any of these or anti-commute them, which would amount to exchanging these indices, we'd get a minus sign, which is properties that this thing has. So we know it should be proportional to this. And it's just a matter of finding out the constant of proportionality, which we can do by just evaluating a specific case. So if we take that mu nu rho sigma or 0, 1, 2, and 3, and we get this equation. I've written the proportionality constant is A. As it turns out, epsilon 0, 1, 2, 3 is minus 1. And then this is, so gamma 5 is I times gamma 0, gamma 1, gamma 2, gamma 3. So this is gamma 5 divided by I, or minus I times gamma 5. So this is minus I gamma 5 squared, but gamma 5 squared is 1, so I just get the trace of minus I times I4, and the minus signs cancel, and so I get a 4I. So that's my A, and that just tells me that that's my constant of proportionality, so this trace should be 4I times this. And so this thing is equal to this.